Okay, students, we're going to be taking a look at some of these graphs. I know I could always just put these graphs in Desmos and get some answers, but I'm going to show you how you won't have to type them all in Desmos. It can be very useful on multiple choice especially, not to have to type in every single equation and to kind of avoid it. So if you have not already read over the notes I have attached to today's lesson, please go ahead and do that before you continue on with the video, and that'll help you understand more of what I am talking about. But if you have read the notes, this first equation here, you can see it has a degree of 3. By degree, I just mean the highest exponent of the graph, so in this case, it's a 3. Now, if it's a degree of 3, 3 is an odd number, so this is an odd degree, so I expect this graph to have end behavior that does not match with each other. The end behavior is just the pattern that the ends of a graph make. So in other words, if it's odd, if one side is going up, the other side will be going down. So in this case, I would be looking for a graph that goes up and down. So this is a possibility, as is this one here. Those are the only two possibilities for graph A. We'll come back and talk about how to make a final decision between those two in a minute. For B, if I have graph B, you notice it also has a highest exponent that is 3. So this is odd, but notice this one has a negative in front. In fact, that could be written as a -1. That is a leading coefficient of -1, and with a negative leading coefficient, that means eventually that graph's going to start going up and down. Going down. These polynomial graphs can go up and down. They can have a lot of different bends and curves going on, but eventually, in the end, that one is going to have to turn around and go down as it gets to the edge of the graph because it has an odd degree of 3. So I'm needing it to be going down at the end, which makes B a possibility, or D. But remember, we just said if the degree is odd, they have to go in opposite directions. So if this side is going to go down, the other side is going to have to be going up. So this end behavior would be up, down, and the only one that would work for that is D. So I know for sure that B matches up with graph D. Equation C, that one has a degree of 4. The highest exponent is 4. And then once I know my highest exponent is 4, that's an even number, so the two ends are going to have to match. So one might be going up, the other one might be going up. That would be a matching degree, or they could be both be going down. That's what I mean about the ends matching. In this case, my leading coefficient is negative, so it's going to turn out that both ends of the graph have to go down, so the only thing that's left for that is answer choice B. As I continue to go on, I can try this one. You notice it's an even degree, so the ends have to match. This time it has a positive leading coefficient, so it's going to end up going up on this end, and since they match, it's going to go up on this end as well. And the only one that seems to do that is graph F, or perhaps graph C. And we'll talk about how I know it's F and not C in a minute. For this one, just an x to the third. Once again, an odd degree with that exponent of 3. So it's going to be, the ends are going to be different. So in this case, one's down and the other's up. What I'm going to have there, now you notice A and E both had a degree of 3. They both had the same end behavior. To narrow it down, basically, since this just has one term, it's basically going to move in one direction the whole time. So E is the graph that moves in one direction the whole time. A is the one that kind of has a little bit of a curve, and we'll talk more about how to know exactly when it curves, where it curves, and how it curves later. But just be aware that if you have a single term, it's going to go in basically a simpler graph. And then this one with some extra terms would be the more complicated one, so I can do that. If you cannot make that call just looking at the equation, the good news is I would only have to graph one of these equations to narrow down which graph went with which, since A and E both pair up together. The last one I have is graph F. Graph F, you notice, has to go with C. So F has to go with C. And once again, although it has the same end behavior as graph D, they both were a 4 with a positive leading coefficient. Once again, I know this one goes here because that is the more complicated graph, and I know that my other one goes here because that is a simpler one-term graph. So hopefully that'll give you an idea of how to use some of this stuff you read in your notes about degree and leading coefficient and to match it up with end behavior. Now, one other thing on the end behavior that is worth mentioning is you have the ability to describe it not only as up and down, but as approaching infinity and negative infinity. In this case, if it's going up, it would obviously be a case that you would say it was going toward positive infinity, and it would be that the y value is going toward positive infinity. And if it's going down, we would be meaning that the y value is going toward negative infinity. So that's the way you can describe that. Now, in addition to describing the domain with the y values, a lot of times in behavior with the y values, we'll also see the x value, the domain listed. So that will be x is as x approaches negative infinity, y approaches negative infinity, and then as x approaches positive infinity, y approaches positive infinity. Basically, this thing about x approaching negative infinity, all that means is that you're talking about this edge, your left edge of the graph where x is negative infinity. As x approaches positive infinity, you're talking about the right edge of the graph. And on y, as y approaches negative infinity, you're talking about the bottom edge. And as y approaches positive infinity, you're talking about the top edge. So you have negative infinity for x is left, positive is right. For y, negative is down, positive is up. Hopefully that helps you understand some of what's written. And we'll look at a couple more examples in just a second. On page 31, they have some graphs. So for those of you who are more visual, you can see the graphs that are summarize what we talked about. It points out that the degree of the function being odd and the leading coefficient positive, it's going to go up in both directions on the positive end. As x is on the right, as x is positive, the y value, the f of x value, is also positive. On the other end, is on the left side, as x goes negative, the function value also goes negative. So you can see on each of these, won't take the time to talk through each of these, but it's the same basic idea. It relates to the degree, the leading coefficient, and gives you a picture, and it even gives you this notation that you are going to need to get used to. And once again, like I mentioned on the other graph, you can, if it helps you can label your x-axis at negative and positive to understand what it's talking about, and you can label your y-axis as negative and positive as well. These next examples on page 32, you're going to, it has several different things. One thing it mentions is standard form. Then it says degree. By type, it means is it even and odd, and then leading coefficient. Well, standard form, remember, means to go from the highest exponent to the lowest exponent. And when you rewrite this, you will move the number. The number moves with the variable. So when I move this around, I don't just move the x to the fourth, I move the entire negative 3x to the fourth. Then the next highest term is this x squared, so I'll have a plus 2x squared. And then the next term is the plus 6x. And then the lowest degree is the 1. The 1 is actually a constant term. And when I see that 1, that lets me know that I do have a y-intercept that is equal to 1. So if I was to graph that, I would expect it to cross my y-axis, my up and down axis, with a value of 1. So you can very easily look at a polynomial function in standard form and say that last number, the number by itself, is the y-intercept. And this first number, the leading coefficient, the negative 3, has to do with end behavior. Since it's negative there, I know it's going to end up at some point going down. So I've already figured out the negative leading coefficient means the end behavior on the as x approaches infinity is going to be going down. And then I can also use my degree. My degree is 4. Since my degree is even, the two ends of the graph have to match. So we said this end has to go down. The end as x approaches negative infinity on the left also has to go down. So I have end behavior going down on both sides. And then the type is it's an even function. Anytime it's an even degree and the two ends of the graph match, I'm going to call it an even degree. And then a leading coefficient, we've already identified that, so that's everything we had. I'll give you a second to try. Why don't you pause your video and try 2 to 4, and we'll go over the answers to them in just a second. Okay, number 2 is already in standard form. There was no need to rewrite it. And when I go for my answers, this is a degree of 3, so my degree is 3. My leading coefficient is this number in front. It would have been my negative 3/7. it would be the entire fraction as my leading coefficient, and this is an odd function. If you were wanting to talk about the end behavior on this one, since it's a negative leading coefficient, it's going to end up going down eventually. Since the degree is odd, the other end has to go in the opposite direction, up. The odds, the ends don't match, the evens they do. On number 3, this one, the degree is a 1. You have an understood exponent of 1 there, so a degree of 1, that is an odd function. If you were looking at the end behavior, it would go up on this side because it's a positive leading coefficient of square root of 15, so that means it would be going down on the other side. And then this number here, of course, is my y-intercept. On this one, to put that in standard form, I would need to move it completely backwards. So I would actually start with my negative 2x squared. Then I would have my plus 3x. Then I would have my negative 2 square root 3. Once I have those in the correct order, my leading coefficient is the number in front, negative 2. Leading coefficient that's negative means the graph eventually will end up going down. In this case, my degree is 2, and since that's an even number, the sides match, so it goes down on both ends. I would have this weird y-intercept of negative 2 square root of 3, and while we're talking about it, anytime you have something like that, if you were trying to graph it, you could always put it in your calculator to find out exactly where it would be crossing the y-axis to get a decimal equivalent. Okay, that's how you can use end degree and leading coefficient to help you figure out some end behavior. On these, when it's wanting you to evaluate, all you really have to do is plug this 2 in for every x value. So I could just take the 2 and substitute it in for every x value, but I'm going to show you also a very neat trick with Desmos. We may have mentioned it once before, but it's a good thing to know how to do. If I wanted to do that, I'd replace every x value with a 2, simplify them all, and get that. You'd probably reach for a calculator anyway, though, so I'm going to show you a quick way to use the calculator. So once I have my Desmos pulled up, I can just type in the equation, which was negative x. To get an exponent, I can do Shift and my 6 key. If I'm using a keyboard, Shift and 6, that little TP-looking thing is called a caret, and it lets you type in an exponent. Or I'll show you the other way you can get an exponent if you're using a mobile device or just don't want to use the Shift key. So minus 2x, and then to get an exponent, I can also show the keypad, and I can get an x squared there, or if I want any exponent, I can click that and just type in the 2 manually. So I've got the shortcut for x squared, or to get a cube or a different exponent, I can use that button there, or Shift and my 6 key. Then I'm going to finish typing negative 3x plus 4. And what I want to know is I want to know the value when it's 2. There's 2 ways I can do this with Desmos. One way is I can turn this into a table, and then I can see the value when it was 2. Or if it wanted a bigger number like 3 that was off my table, I can always type in a number manually. Desmos makes it very easy to get the answer. The other thing I could have done is I could have typed in an f of x in front of this, and basically given my function a name, just say, hey, this function is called f. Maybe you want to think of f as being Fred. So function Fred, if I plug a 2 into it using my f of x notation we talked about in the last chapter, it would evaluate. So that's a quick way to use Desmos to evaluate, since you were going to have to type it in the calculator anyway. I like to type in the equation as is, and then if I need a graph or if I need a different value, it's very quick and easy to change and get whatever other value I need by just changing that number.